Hello. Good afternoon. Keep coming in. Welcome. Thank you for coming along to this session. My name's Steve. I'm a Microsoft MVP, Pluralsight author, and engineer at Elastic. You can find me online. I'm at Steve J. Gordon on most social platforms. I blog at stevejgordon.co.uk. Some of the stuff that I'll be going through today is kind of built off of longer form blog posts. So if you want to dive a bit deeper, check out those articles. This bit.ly link here, if you want access to the slides, the code, and things after the session, just grab that link or the QR code there, and you'll be able to kind of review those. I'll share that link again at the end. So today we're going to be talking about high-performance C# code and some of the, I call them new, they're not new anymore, but newer features available to us in the language and the base class libraries that allow us to do high-performance code. So just to set the agenda and make sure we're all on the same page. What we'll be covering is, we're going to begin with just a quick discussion around what is performance and what is it we're actually aiming to improve in our code. Thank you. We'll then spend a little bit of time talking about how to actually measure the performance of code so that we know where we're starting from and where we're actually moving towards as we do some optimizations on some code. We'll then spend a bit of time with these types, so span of T, read-only span, and memory of T. We'll talk a bit about ArrayPools. We'll talk a little bit about pipelines, system.io pipelines, and a type called read-only sequence. And hopefully, there'll be time for me to race through some stuff on System.Text.Json at the end and just show some demos of using high-performance stuff there. So let's begin really with the aspects of performance. So there's three main sort of categories or criteria of performance that I tend to think about when I'm optimizing code. The first is execution time. So how long does a unit of code take to run? That might be, the entire operation of handling a request, for example, or it might be that you're looking at smaller units of code, individual methods, or even lines of code, and how long those take to execute. Typically, if we can make our code execute more quickly, then we can give a better response to the user, the customer that's visiting the site or using the application, because we're able to return results or information to them more quickly. Throughput is a sort of related measure, but it's a better way of thinking about this in terms of what a system or a service can actually achieve. So throughput is more a measure of what we can actually do with a given amount of resource on a machine, so requests per second in ASP.NET Core, or maybe messages processed off a queue per second per minute, however we're measuring that. And this gives us a nice way of measuring sort of the actual performance of an application in production, because it's an easy measure that we can take using metrics-based tools to collect this information to see how our applications are performing. These two are quite closely linked. Typically, if we can reduce the execution time of our code, then we might see that we're able to increase the throughput of the system as well. It's not always an exact correlation. Different things can affect throughput. There's different sort of bottlenecks that you might encounter on your system around I/O and memory that may sort of play a part in that measure as well. But typically, if we get the execution time, we see improvements in throughput. And then the final one that not everyone tends to think about is around memory allocations. So allocations in .NET are extremely cheap because we already have the heap memory sort of ready to go. And so when we create a new object, it's usually just bumping a pointer logically within that sort of heap memory. The cost for memory allocations comes later. At some point in time, those objects go out of scope, and that memory can be reclaimed. So at some point, the garbage collection process is going to need to kick in and clean up those unused objects. And that tends to have a small, but sometimes significant performance impact in high throughput systems. And so if we can avoid allocating objects on the heap and allocating memory at all, then we avoid that potential penalty later on. And a lot of the stuff you see, if you read any of the posts by like Stephen Taub from Microsoft, when they talk about like the high performance features that they've introduced, they'll often be demonstrating how they've reduced allocations as one of the ways that they've made performance overall better. Now, I do like to caution that performance is contextual. There's various different ways of saying this, but I just sort of summarize this in this form, because a lot of what I'm going to show you today isn't necessarily stuff that you need to race to your office on Monday and start implementing. But in certain situations where you've got high throughput systems or you're already encountering certain bottlenecks in your system, then you might want to start looking at optimizing some of the code to reduce those problems that you're facing. But maybe for 95% of applications, some of the stuff I'm going to show you today might not be necessary. Although what I do hope to demonstrate is that some of the techniques to, for example, reduce allocations don't necessarily require a lot of deep advanced code to write them. Sometimes we can actually achieve those gains with relatively simple changes. That said, there is a bit of a trade-off when it comes to high-performance code. Typically, the high-performance code tends to get a little bit more verbose. It's a little less easy maybe to read or reason about because it's written in a certain way that we know optimizes for certain scenarios. And that can mean that it's harder to maintain the code that we've moved to this higher performance environment. And so you do have to have this trade-off. Like if you're working on a system that's regularly changing, it has lots of developers touching that code on a regular basis, then you might want to move more towards readability and maintainability as your priority, because actually getting out features, shipping code, is more important than sort of milliseconds of execution time or small amounts of memory gains that you might make. But there will always be a certain set of applications where if you can reduce the memory footprint, for example, of the application, you might be able to reduce costs in terms of how you have to scale that application in production environments. So you need to weigh this up in your organization, service by service, to see where you should be sort of treading across this line. Are you moving more to the high performance, or are you needing to just keep that code easy to work on and easy to read? So when we go around optimizing code, I'm going to be sort of demonstrating what I refer to as the optimization cycle today. And the most important first step in optimizing code is actually making measurements first. It's very dangerous when you're doing optimizations to make assumptions about how code might operate if we switch to a higher performance code that we've already used maybe elsewhere. It doesn't always pay off in the way we expect. So we start by measuring our code to get an understanding of what the system's currently doing. And the very first set of measurements should be ideally production measurements, if you can. So how is your system currently functioning if it's already deployed? What is your throughput of a web server, for example? Or how many messages can your processing service manage off a queue in a certain given amount of time? You want to make sure that any changes you're making aren't negatively affecting those production metrics. Then when we start actually looking at where we should be spending our time in our code, we want to start with sort of higher level tools that allow us to profile CPU and memory to start to give us a sort of guidance of where we want to start optimizing code. So we'll talk about a few of the tools in a moment, but the basic idea is we want to know what are the hot paths in the application so that we can go and focus on where we could improve that code base on those hot paths, because that's going to give us the most gain if it's code that's executed most often. And we can use memory profilers, for example, to then help us narrow down within that hot path where are the potential gains for maybe reducing allocations coming from. And then we go down to even lower level measurements. And we'll have a look at an example of benchmarking with a tool called benchmark.net as we move through the session. And this is what allows us to get very high precision measurements for small units of code as we go about optimizing it. So we measure first, we get our sort of baselines, and then we can begin to optimize. The most important thing about this step is that we don't just make all of the possible changes that we can think of in one go. I prefer to do this in small iterations, small changes. After we optimize maybe a few lines of code with a high-performance technique, maybe like one of the ones I'll show you today, we want to measure again to validate that that change is actually represented in the data that we're seeing. If you change a whole bunch of things together, you might improve the overall performance of your code, but you don't know if all of those changes were actually positive. And so by doing things in small increments, you can get very scientific about validating each theory that you have, and each change that you're making is pushing you towards whatever goal it is you're working toward. And then this cycle just continues. There's no real specific end point for this that you have to determine within your organization, within your team, what is the point to stop optimizing. Sometimes you'll have reached your given requirement. You may have reduced your memory footprint by half, and you're happy. And that's fine. That's a good place to stop if that was your objective. Sometimes you might just hit the ceiling of what you think you can reasonably achieve. You've gone through all of the techniques that you've read about or seen today, and actually you don't think there's any more real gains. You're talking sort of nanoseconds or maybe a few bytes here and there, but there's not a real gain to be had. So you don't want to continue optimizing too far past that sort of optimum point of time spent versus the gains that you're making. So how do we measure high-performance code? How do we sort of start to analyze some of this stuff? So the first tool I like to highlight, just because it's often overlooked, is if you're using Visual Studio, and I do, then the diagnostic tools that pop up when you start debugging an application can be quite useful. They can give you a bit of a representative view of how the memory profile of that application is looking. You can see where the GCs are occurring. You can take snapshots of that memory if you want to understand a little bit more about it. And so just by sort of debugging our application, we have access to some rich data. The caution here is that you are in a debug mode. You're not running this against highly optimized code, so there might be some differences to what you would measure in a production application. So it's a good indicator, but it isn't necessarily a final measure. For that, what you want to do is start going a little bit deeper on the release build code and actually use tools like the Visual Studio Profiling Suite or Purview or some of the JetBrains products to actually narrow down further. Visual Studio profiling tools are actually pretty rich today. We have a lot of options in there. We can look at all of the memory allocations, tracking those across time to see what's being allocated. We can profile the CPU and see where the method times are being spent. And we can also dig into things like the async and the task parallel library parts as well. So you can actually get quite rich information just from Visual Studio. The other end of the scale, I would say, is Purview. This is a very rich tool. It's a very advanced tool. I don't get along with it particularly well. I've dipped in and out of it, but it is quite difficult to get to grips with. And so I don't recommend it as kind of the first thing you go to unless you really feel you need to, or you've had some familiarity with it in the past. Where I tend to push most of my time for performance stuff is into the JetBrains tools. I'm not paid to say that. I don't work for them. I just prefer them. .trace, .memory are both very easy tools to get started with in terms of taking CPU profiles of an application, as well as understanding where the memory is being allocated and diving into that information. So pick the tool that you like. Sometimes, not always, it can be useful to go quite deep. And this is where maybe you might want to start even looking at the intermediate language code that gets generated when you compile your C# application. Sometimes this can give you a bit of an indicator in terms of the C# you're writing, how many IL, intermediate language instructions, is that actually compiling down to. And typically, if you can make your code smaller and have less instructions, then it's going to execute more quickly. Other things we can sometimes spot in IL-based tools is we can see where boxing instructions, for example, are being occurring, so we can maybe identify cases where we're boxing value types as well. So not always needed, but there are various free tools out there that you can use just to go and inspect that IL code. And don't overlook the importance of having production metrics and monitoring in place before you start doing this as well. Again, testing this stuff locally, even if you try your hardest, you might not always get a representative example of how an application performs in a real production environment. Because our developer machines are a bit different, there's no real contention going on. The loads that we're putting through them are typically not necessarily going to be the same as we would see in production. And the patterns of usage might differ as well. So having monitoring in production for existing applications before you start this journey is pretty useful. Just basic things like maybe measures of memory, CPU usage, throughput of an application, if it's an ASP.NET Core type app, can be really useful because you can see if you're positively or negatively affecting them in the direction that you hope you are. So the tool that we'll spend a little bit of time with today, just because less people are familiar with it, is benchmark.net. So this is a library for typically micro-benchmarking our code. So this is where we all want to measure small chunks of code, maybe individual methods, maybe even individual lines of code, and compare them to how they're sort of working after we've optimized them. It's a highly precise tool, so it does a lot of things to give us accurate measurements. Technically, you could just use like a stopwatch or a timer around some code, and that would give you a rough measure. But what benchmark.net is doing is it's going to run many different stages as it goes through benchmarking. It does a warm-up phase to make sure that the code you're testing is pre-jitted, so that the just-in-time compiler has run through its various tiers, compilation levels, and your code is the most optimal that it would be in a real scenario. It runs its own overhead measurements, so it checks how its overhead of actually inspecting and monitoring your application while it's running might take into effect, and it can remove that overhead. And then it will run each of your benchmark methods many tens, hundreds of thousands of times to make sure it's giving you good statistical averages for the data that you're measuring. So when we start getting down to those kind of nanosecond tiny measurements of time, we need that highly precise measurement process to make sure that what we're getting is accurate. There's various other pieces of data that we can collect in the form of diagnosers. So we'll see one in action shortly, but these are things like GC and memory. So we can change the GC mode that we're running our benchmarks under. We can look at different JIT modes and things. And this can be useful. Sometimes we can then replicate more closely what would be a production system when we're doing our benchmarking. We can compare performance on all the different platforms as well. So you might be developing on a Windows machine, but you might be running your benchmarks against Linux mode as well, and you can run these then in CI and compare how those things run. This tool is the tool that's very extensively used by the Microsoft teams. You'll see it in all of Stephen Taub's kind of annual performance blog posts, and it's been used heavily through the .NET runtime code base as well as ASP.NET Core as the teams have been optimizing those. So this is kind of the hello world of benchmarking. So up the top here, we start with a main method, and that's just invoking this benchmark runner.run method. And in this case, what we're doing is passing in a type that contains some benchmarks. Now, there's various different ways that you can configure benchmark.net to run. You can have it in kind of an interactive mode where it discover all of your benchmarks in a system and let you choose what you run. You can have it in a more CLI mode where if you're doing it in sort of CI environments and you want to run specific benchmarks, you can do that by passing in the name of those as arguments. But in this mode, we're just going to run everything that's in that class below, the name parser benchmarks. And what I've added here is that memory diagnoser attribute, which allows us to say that in addition to execution time measurements, we want to do a run that measures the allocation overhead of this code as well. I have a little bit of setup code here. So these are set up as constant or static pieces of data. They're not things that I'm actually measuring as part of my benchmark, but they're things I need to do the benchmark. So I need some input data, and I need an instance of a name parser. And then my actual benchmark is below. So it's just a regular method with the benchmark attribute applied to it. And in this case, we're calling the getLastName method of that parser, passing in a full name, and we're going to then see what the execution time and memory overhead of that particular method is. We're going to run this. It's going to take some time to run. You want to do it on a release build. You also ideally want to do it on a system that's not running other stuff. So in an ideal world, you disable every other application, even maybe antivirus, because all of those things could kick in and affect nanosecond level measurements. But generally, as long as you've turned off most of your other apps that could consume memory or maybe jump in and affect CPU scheduling and things, you'll get fairly accurate results. And after a few minutes, because of all those warm-up phases, all of those many executions that it will do, we end up with this basic summary results. And there's a much richer set of results that you can pull from the output folder. But in this case, what it's giving is a quick summary of that particular method takes 116 nanoseconds to run. Now, we don't know if that's good, bad. It's pretty fast, but could we make it quicker? Do we need to make it quicker? That's a decision for us to decide later on. Because we added the memory diagnoser, we have a few extra columns on the end. So in this case, we have a single column for Gen 0, which is a rough approximation, as best it can kind of estimate, of how many, per 1,000 operations, how many Gen 0 collections would be incurred. So in this case, we're saying that you'd have to run that method roughly 29,000 times to have induced enough pressure of Gen 0 objects for that to then need freeing. It's not an exact measure because the GC uses a bunch of heuristics and sort of adaptive technologies behind the scenes to try and make it as efficient as possible. But it gives you a bit of an indication. And the fact that we're not seeing a Gen 1 or Gen 2 column here shows us that none of our objects are long-lived or particularly large necessarily. We can see how many bytes was actually allocated as a result of calling that method. Again, we don't know if this is good or bad, but we do know that we've got 144 bytes allocated by this particular method. So this would be a good starting point for us. So now that we've had a brief introduction to sort of benchmark code, let's look at some high-performance code, and then I'll hopefully show you some demonstrations of where I've applied that in the past and how I've made those gains pay off for me. So the first type I want to spend probably most time on is span of t. I'm always curious, how many people in the room would say that they've heard of this span of t concept already? By show of hands. Maybe half-ish? How many people have used span of t in their own code base so far? It's not bad, but far fewer. And I've been doing this talk on and off for probably 4 or 5 years now, and it's pretty much always the same proportion. A lot of people have heard of span of t, or a reasonable number, because it's always mentioned in things like those annual blog posts by Stephen Taub. It's always mentioned quite heavily in any post that discusses performance in relation to .NET and the runtime base class libraries, because it was quite a revolutionary addition to .NET that has led to many improvements to the runtime that we've seen since .NET sort of 3.1 sort of time frame. But I also find that not many people have actually used it in code, partly because they may not need to, but also partly because I think Microsoft tended to caution away from using it. And I've always been a little bit less on the caution side. It's not hugely complex to get started with span of t, and you can apply it quite easily in code bases to reduce allocations, as we'll see. So this was built in .NET Core 2.1 and since then, so we've got it on all latest versions of .NET sort of runtime. It's also available as a system memory package, so you can actually use this with .NET Framework applications and .NET Standard libraries. There is a subtle difference in the level of performance. So in .NET Core, what they did is actually make some runtime changes to optimize for this type in the best way possible. We don't tend to see runtime changes in .NET Framework, partly because it's mostly maintenance mode and partly because of fears around how that ships. But with .NET Core, we have a much easier system of upgrading and running side-by-side versions. And so they felt safe in actually optimizing this with actual runtime changes. At its heart, what it does is provide a read-write view over some contiguous region of memory. The nice thing about span of t is it's kind of agnostic to what that memory is. So we can actually use this over traditional heap allocated memory, so things like strings or arrays, which are contiguous blocks of memory off the heap. But we can also use it to reference memory that's allocated directly on the stack, and even native and unmanaged memory if you're working in those types of environments. But we work with this one type that's both type safe and memory safe in all of those scenarios. So one of the key things it offers to us is this ability to avoid allocations and data copying, which can be quite significant in reducing the overhead of application code. So we can work with it in a very similar way to traditional array-based data structures. We can index into it. We can iterate through that data. There's pretty much almost no overhead versus using a native array. And all of the operations on here have been highly optimized to be as efficient as possible, which is why it's used throughout the runtime libraries. One of the key operations on span that's the most valuable, really, is this idea of slicing data or slicing memory. So here what we do is we start by creating a new integer array of 9 elements, and then we call as span on there to get a span of t, a span of int in this case, over that data. And so these two local variables here would point to the same portion of memory. The first thing you might worry about is this creation of this span of int that we're creating as a result of that new as span call. The thing about span is it isn't ever allocated on the heap, so there's never any GC overhead from creating an instance of a span. It's a specialized type that only ever appears on the stack. And we'll see later why that introduces some limitations, but it also offers this guarantee that actually it's a very cheap thing to do. There's never any heap cost that we should be worrying about. Now, once we have that span-based view over the data, at any point in time we can call slice on there to give us a different view over that same block of memory. So in this case, we're slicing into a starting position of 2 and a length of 5. And so this new span 2 here references a different portion of the existing memory. We haven't done any data copying. We've just changed our view. And this is extremely powerful if you're processing bytes that maybe are streaming off the wire, or you're processing through large strings, which are just, ultimately just characters in a system, because you can just change your view over that data very quickly. The nice thing about slicing is it's a constant time, constant cost operation as well. So it doesn't matter if this array is 9 elements or 9 million. The cost of slicing into it for any length is pretty much exactly the same each time. And that makes it very powerful. Because we're never copying anything, we're basically just holding a pointer within that memory portion. And then the length, that's pretty easy to maintain. The analogy I use for slicing, if it hasn't quite sort of fit into your mental model yet, is of maybe taking some photographs. So I've been out in Porto, we've been taking some photographs around the city, and sometimes there might be a building or some piece of architecture that we want to get a nice close-up picture of. And one option we have is to walk closer to the object, and once we're close to it, we can take our photo. And depending on how far away that object is, it might have taken us a fair amount of time, a fair amount of energy to get there, but eventually we will get our close-up. The alternative on our phone is that we just pinch zoom. And ignoring the fact that we have, potentially some degradation of image quality that doesn't come across in this analogy, The key thing there is a pinch zoom is pretty much a constant time, constant cost operation. We can very quickly change our field of view over a scene, and then we have a different view of that same scene from the same position with very low effort. And that's kind of the idea with slicing. So I'm going to begin with a brief overview of what it looks like to optimize some code. Now, this particular example, I do caution, is very contrived, very trivial. This is just to get us started, and then we'll look at some more real-world code later on. So let's imagine on Monday you return to work and your manager tells you that if somehow that they found a way that if you could have a method that takes an array of elements, even number of elements, and then starts taking a quarter of those elements from the middle, you're going to have some major business advantage over your competitor. So let's imagine that's the scenario you're given. One pretty reasonable way that you could achieve that without thinking too hard is, okay, well, we'll get the length. We'll skip halfway into that array, we'll take the number of elements, or a quarter of the elements, and then we'll return the new array. And that's perfectly valid code, it will do the job. But then maybe your manager comes to you and says, actually, if we can make this code really, really fast, maybe we can make a huge amount of money. So I told you it was contrived, but let's go with this. So the first thing we should do in this scenario is measure. Before we even begin optimizing, we want to start with measuring our current assumption. And so what we do here in this benchmark is there's a few new elements that I'll introduce. So again, it's still a class, but this time we've got this size property on here with the params attribute with 3 different values. What this lets us say to benchmark.net is that we want to run these benchmarks with these 3 different values for that size property. So run these benchmarks 3 times, essentially, with those different sizes. And this allows us to kind of test edge cases. Sometimes testing your kind of expected value is fine, but maybe there are edge cases to what your system accepts that actually might result in different measures of performance. And so by testing your kind of middle case plus your edge cases, you can make sure that you've got a representative view that the changes apply in all scenarios. Because we're setting this up, we now need an array of these different lengths as our input. And so what we do in this global setup method here, which is just a regular method with the global setup attribute, we can pre-create that array of the right size and populate it. This runs once before the benchmark run actually kicks in, so there's no measurement overhead here. This isn't part of what you're measuring as part of your benchmark. It's just setup code. And then to do the actual benchmark, we can just run that piece of code that we saw earlier. The only difference from what we looked at earlier is that we're now putting this baseline equals true to say this is our starting point. And once we run this, we see that, OK, for an input array of 100 elements, it's about 100 nanoseconds, 224 bytes allocated. And we see what we'd kind of expect, given the code. If we reason about it, as we increase the input array size, then by factors, the execution time and the allocations are going up, because we're creating a new array at the end of the day with that new data in it. And so that's giving us our starting point, our baseline. So maybe the first theory we have is, well, we've heard that link has some overhead to it, and maybe we should avoid using that, and that will make our lives better. So in this case, what we do is create a new array pre-sized. We then use array copy to copy the data from one array to the other, and then we see if this works better. So we run our benchmarks again, now with our new version added. And we can see that for 100 elements, it looks pretty good. We've reduced our execution time by about 86%, and it looks like our allocation ratio is improving massively as well, by 43. The good thing is we've tested other sizes here, and we can see that while the execution time is still a good improvement, the allocation ratio is getting less and less valuable. And that's because all we've done is remove the small 96 bytes of overhead of using that link expression versus what we're doing with the array copy approach. But we're still creating a new array. We're still copying data in there. So in this final example, let's assume that we can change the return type. So I'm changing the return type here to a span of int. So let's assume that there's further processing that happens after this occurs, and our callers can accept a span of int back. So in this case, we now use the as span, and then we can slice in. You can also use the range operator here if you prefer the syntax, so you don't need to slice. You can just do square braces, ... length, and that's quite nice as well, or starting position and end position. And so in this example, we now moved to kind of a span-based approach. And we'll see that now the execution time is 99% improved, so we're less than a nanosecond, which I think most people will agree is pretty reasonable. And the allocation overhead now is 0. We've not got any bytes allocated, because all we're doing is returning a new view over that existing array from that start position halfway in for that length of a quarter of the elements. And we can see that as we move through the different sizes, this constant time, constant cost operation of slicing, doesn't matter how big that input array is, the savings are the same. And so this has now massively reduced that portion of code's overhead. As I say, a little contrived, but we'll get to some better examples soon. Now, the other nice thing we can do with span is we can work with strings. So on a string literal or a string variable, we can call as span. And we get back a read-only span of char. So char is fairly obvious. Strings are made up of characters. The read-only span, because the runtime will enforce the safety here that strings are immutable. So it's never going to allow us to get a read-write view with a span over the memory occupied by a string, because that would let us effectively mutate that string's data, and that would break pretty much every assumption we have in our code base about safety of strings. So we get back a read-only view. And so this still is useful because we can parse through the existing strings, finding the pieces of data that we want. So in this, again, very basic example, maybe we just want to get the portion of that string that represents the surname so that we can do some further analysis on it. In this case, we could say, let's find the index of the last space character and then slice from that position onwards. And now we're still working with the same block of memory, but we're able to do it on strings as well. Now, there are some limitations of span of t that are worth pointing out. And as I go through these, you might get more and more concerned about where this can actually be applied. But don't worry, it is fine. So the first thing is, I mentioned earlier that the guarantee that we have that a span is never going to end up on the heap. So we can use it safely at any point in our code without worrying about heap allocations. And that's enforced by the fact that it's not just a normal struct. It's actually got this ref struct keyword that was introduced in C# 7.2 that enables a kind of guarantee that the runtime will enforce that this type can never end up on the heap. Because there's various ways that a value type would end up there. And so what this effectively means is we can't ever let a span of byte or a span of int or whatever it is be boxed, because that would be then stored on the heap. One of the main reasons for this limitation, this kind of stack-only limitation, is that it can be pointing at stack allocated memory. So we can never allow this span of t thing to live longer than the stack frame that it is used on, because it might then be pointing at data that's no longer valid if it outlives that stack frame. So that's one of the reasons we can't do boxing. It also means that it can't be used as a field in a class or a non-ref struct, because again, that data is living on the heap. This is the one that tends to trip people up. Because of the way that async works, it can't be used as an argument or a local variable in async methods, because async methods behind the scenes eventually get compiled down to that state machine that you may or may not sort of be aware of. But on most code, that will be a struct, but it's still not a struct that's guaranteed to be stack only. And so for the same reasons that it can't be a field in a class, it can't be used in those environments, because those basically get hoisted up as fields on that state machine object that gets created. For a very similar reason, it can't be captured by Lambda expressions because of the closure that would be created around those. And up until this version of .NET that's coming sort of in November, it couldn't be used as a generic type argument. Now that's actually that limitation is being removed because we're getting this new sort of new combination of keywords as a where constraint on generics, where we can say we do allow a ref struct, as long as we know that our method is never going to let that escape the safe context of being within the same stack frame. And so in C# 13, you can start to use it in certain new environments. And there's other limitations I'm not even starting to hint at here that get much more sort of deeper about how this functions. But the key thing is that there are some limitations to it. Fortunately, at the same time as introducing span, the team introduced this other type called memory of t, which has very similar semantics to span. The main difference, though, is it can live on the heap if it needs to. So it's defined in a different way, which does make it a little less versatile, because you can't necessarily point it at stack allocated memory anymore. And the performance is not quite as good. There's certain guarantees about the stack-only nature of span that have allowed the runtime to be modified to make it highly efficient, and we don't get all of those same guarantees with this memory T version. So it's defined in the code as a read-only struct, but not a ref struct. So we still generally don't see it being copied too often, hopefully, but it might eventually end up being boxed in certain scenarios. Because of that, if we're working with it directly, then it's going to be slightly slower if we do things like slicing into it. But fortunately, at any point in time, we can call span on there and get the span property, which represents the span-based portion of the same block of memory. And so this kind of comes into effect if we're trying to do something in, say, an async method, and we'd really like to take some data in this new sort of highly optimized form. If we try and pass a span of byte here, then we get this compiler error because we're now trying to create this parameter of a type span. But what we can do instead is switch our code to accept a memory of byte, and we're still fine. And things like a byte array, etc., will sort of implicitly convert to this quite happily. And that means that we could just work with that memory directly. If we're not sort of worried about the sort of the final nanosecond of performance, then usually working with memory is reasonable. But if you want to, what you can do is create a non-async method where you can accept a span and then switch to that at any point in your code that you can do so. So typically, we're only in an async context during some I/O operation. We're getting some bytes off the wire through a stream, or we're reading in a file, or whatever it might be. But once we've done that sort of initial read and we've got some data buffered into memory somewhere, at that point we can switch to non-async code while we're processing. And so in this code base, one option you might be tempted to do is try and create an instance of a span sliced at a certain point that you're going to pass into that async, non-async method, which again, you can't do because it can't be a local. But what we can do is pass in that slice expression directly, and the compiler's totally happy that it can make all the right guarantees about this now. And then that non-async method can do all of the processing using the high-performance span-based approach, and we can switch back to the async method when we're done. So I'm going to start putting this into practice with a more real-world example. And this is based on something for a project I worked on at a previous company. So I'm going to switch over to Visual Studio, which looks OK there. Is the code OK at the back for everyone? Good, cool. So what I'm going to do is show you, I'll give you the quick summary of what this is doing, actually. I'll show you this slide. So the context for this service, which is a microservice I used to work on, is that we were reading messages off of a queue. In this case, it was Amazon SQS. We deserialized that JSON data from the queue, and we wanted then to store into the Amazon S3 blob store a copy of that message, basically as a backup process. And in order to ensure that we were only storing one copy, we derived a unique object key, basically a file name for that blob, from some of the properties on the message. And so the existing code that we had looked a bit like this. This is sort of simplified down a bit, but we have this event context, which you can imagine represents the deserialized message coming in. In this case, it's got 5 properties. In the real system, it had a few hundred. But the key thing is we wanted to use just a few of those for the object key. So if the date was present, we'd use the date, but it wasn't always guaranteed, hence why this code deals with that possibility. But the main way this code worked is that we basically created a string array to hold all of the parts that were going to be used in that object key. And then for each index of that string array, we use this getPart method to take the input string. So that in this case, for example, this is coming from the product or the site key that's coming off that object. That would come in. If it was null or empty, then we would just fill that particular element with just unknown, because for some reason we didn't have the data. Otherwise, we'd call remove spaces, which just did a replace of spaces with underscores. And then once we'd done that, we did this is valid check, basically, using regex to make sure that it matched a particular set of characters we knew was safe for S3 object keys. So we did that with all of the main pieces of data coming in. We then used the date time toString just to format out the date if it was present. And then we put the message ID and a suffix on that file. So once we've got all of the individual pieces, we just use string join to join them together, lowercased everything, and that then became the object key. So a few of you might have already spotted where that might allocate and why that could potentially be optimized. And so I'll show you the new code up here. So there's a few differences. So this code has been updated for like .NET 8. And so one of the things that I did in here was move to the new source-generated regex stuff, which basically pre-computes the regex expressions and the code needed to do a regex match in an optimal way, and it does it at compile time rather than runtime. So you can remove some of the runtime cost of regex by using it. The other thing it does here is use this kind of special sort of technique for basically defining these read-only span static properties. And what this does is the compiler knows how to handle this and basically treats this as specialized data that gets stored into the actual binary data for the DLL. And so at any time that we're using these in code, it's just pointing to an existing memory location within that DLL, which lets us be very optimal and avoid allocating those when we're comparing. The main bulk of the code then used this new string create feature. So basically what string create lets us do is to pre-allocate some memory on the heap that's going to be used to create a string, but it lets us mutate that memory directly and work with it as a span while we're creating the string. So once it's created, it becomes a regular immutable string, but during that creation method, the code actually can mutate the various bytes or various characters within there. So in order for that to work, it has to pre-compute the length, because we need to know the right length that we need for that string to occupy. I won't show you that code, it's fairly boring. But then we do string create, and what string create takes is this key builder action, which is this special span action type that basically gives us, lets us pass in our state, which is our event context, and it gives us access to a span here, a span of characters, which is that pre-allocated heap memory for the string. And so in here, what we do is for each of those pieces of data that we want to use in the string key, we call build part, and we pass in a current position as we do this, which is what's going to allow us to slice through that memory as we're adding new elements to it. And so we take the input string, and we do basically what the original code is, but we're now doing a more sort of basic check to see if it's null or empty by checking if it's a length of 0 or white space. We then run the source-generated regex for the validation piece. We then call this memory extensions to lower invariant, which lets us take a string, copy the characters out, and lowercase them into our span pre-allocated memory in one operation. Every time we do something where we're writing, we're incrementing our position by how much we've written, so we're slowly moving through that span of memory as we add more elements to it. And basically, we do this for each item. Then up here, we do a span replace. So this new replace operation added in .NET 8 is a very optimized way of replacing certain characters within a span. So we replace all the spaces with underscores. For dates, we can use this new try format or newer try format method, which lets us format a date directly into, again, a span of characters, and gives us back how many bytes were written as doing that. We then lowercase the message ID, and we copy on that JSON suffix. And in this case, we're just slicing, in this case, using a range-based operator for the last 5 characters where we put the suffix in there. So what this is doing is basically moving us to a span-based way of building up that string. Now, I promised we benchmarked and we did all the right things as we went ahead with this, and I'll just show you the results so you can kind of see the gains. So with the new code, we were about 26% quicker. Actually, our improvements were like 3 times faster when we did this back in the free 1 days. I've updated this code a few times to move to new versions of .NET, and Microsoft keep improving even those built-in operations like string replace, for example. So the gain is going down, but there's still a gain to be had by manually doing this. And the key thing is that we then removed about 74% of the allocations, so we're down to 192 bytes. And when we profiled the memory, that 192 bytes was the actual object key string that we were creating, and we had to create to pass into the Amazon S3 API. So that means that we've got rid of all the overhead of creating that. We're just down to the actual cost of the string creation that we actually want. Now, on its own, this might not seem like it's worthwhile. It's a few hundred bytes, right? But this service was doing 18 million messages a day. So this one subtle change to the code base in how we manage this object key creation saved us 10 gig of daily allocations. And that's going to contribute to a number of GCs that we're no longer having to do in that application as a result. So we got quite a nice gain there. So the next type I want to talk about is called ArrayPool. The name kind of gives this one away. It's a pool of arrays. And this can be used anywhere in your code base where you need those kind of like temporary buffers of either bytes or characters as you're doing some processing. Typically where we see this is if we're doing anything within an iteration where we might be working with stream-based data where we have to pass it a temporary buffer to work with. And what we can use the ArrayPool to do is instead of incurring the cost of those temporary arrays each time we're doing that processing work, we can use a rented array, which is coming from this shared pool to avoid that sort of cost. So over time, we sort of amortize away the cost of creating those temporary buffers. So it's found in the system buffers namespace. Renting is pretty straightforward. We access the array pool of T, so whatever type we want an array to hold. We generally use this shared version. So this is a pre-built sort of in-the-box implementation of an array pool that uses a predefined set of buckets for the sizes of the arrays that it can store, and then we just rent the one that we want with the length we need. The key thing is that we might, and generally will, get an array that's larger than what we ask for, and the reason is for a pool to be useful, it has to bucket into particular sizes. It can't have every possible size array that we might ever need, because the chances of us needing the same exact size every time isn't necessarily consistent. So it's going to give us the closest array size it has that's at least big enough to hold what we've asked for, which means that when we're working with an ArrayPool-based piece of data, we're typically then going to need to track the length of the data that we've actually written into that temporary buffer so that we can always slice it later on and just view the portion that we know we've written. When we're done, we return it, we return the array, and we optionally can pass this clear array switch here as well. So by default, the clear array is set to false, which does mean that by default, when you return an array, the data is still left in there as it was when you worked with it before. So for sensitive systems, that might be something you need to think about. The reason this is done is that zeroing out an array has a cost. And so by default, for this to be as optimal as possible, it doesn't zero out those pieces of data. Generally, that's not going to be a problem. But again, if you need to switch to the kind of safer mode, you can do so. So what this looks like is here, for example, imagine we have a method. It's going to be called by some tight loop as processing is being done, and it needs a temporary buffer that it's going to pass into another method. So here we're allocating each time 1,000 bytes for this buffer. We can very easily switch that to instead prefer using the shared array pool and renting 1,000. Now the main difference here is that when we then want to work with that buffer, we now have to pass in the actual length so that we know we're going to only work with 1,000 elements, which is the piece that we know we're going to have populated. Because typically, if we rent 1,000, the minimum size that array pool can give us is 1024 bytes. And it might even be larger if there's none of those available and it moves a size up. And so it does mean that when we're working with the data below, we have to then slice into it for the length that we actually know we've populated in the previous method. We do need to remember to return the array for the pool to have any real benefit. I'm showing it here with a try finally. Microsoft have actually moved away from this guidance fairly recently and tend not to bother with it. So the idea of doing it in a try finally is you always guarantee if there's an exception in that other method, we're returning the array to the pool. But actually, the cost of doing a try finally and the operations needed is usually not necessary for the number of times that might actually cause an exception. So unless that method could really cause an exception very often, it's better to just do the method that you want and then return it afterwards. And in the few cases where an exception were to occur, it doesn't matter if that buffer doesn't go back into the pool. It will eventually, through its finalizer, be collected by GC anyway. So it's up to you. It doesn't really matter either way. I still sometimes do it this way just to protect myself. So the other type I want to show is System.io pipelines. This one's good if you ever work with like streaming data or sort of data coming across the wire. And so this was originally created by the ASP.NET team. I think it was pretty much David Fowler's kind of child that he sort of built into the .NET system. So it was originally in the ASP.NET code base and then has been shifted into the runtime code base. And the key reason it was kind of introduced was around Kestrel. So Kestrel is the web server in ASP.NET Core. It's obviously dealing with lots of bytes coming off a wire that then go through the ASP.NET Core pipeline internally. And one of the things the team wanted to do was try and avoid all of those costs of switching between different streams as that data gets processed through the pipeline. So they found that by moving to this new sort of pipelines library, they could roughly improve their performance by about 2x in the kind of Kestrel scenario. And typically, it's just done by removing what would otherwise be code you could write yourself to manage streams and temporary buffers and use the array pool to try and avoid allocations. But it would actually have a lot of boilerplate and edge cases that you'd have to consider. So it just wraps that all up for you and does all of the heavy lifting. So the main difference is that unlike when you're using streams yourself, with pipelines, it's managing those buffers for you. So you don't create the buffers that you would pass in as you're processing the stream. You just work with this pipe concept, and internally it's using what's known as a memory pool, which basically is backed by an array pool behind the scenes to actually manage those buffers without allocating. Two ends to a pipe, as you might guess. So there's a writing end, and when we write, there's a few ways we can do it. There are sort of shortcut methods for writing small blocks of data directly with write or write async. Or in most scenarios, what you might want to do is actually just ask the pipe for a block of memory. In this case, it comes back as a memory of byte that you can then populate. So it's a memory of byte, typically because pipelines is going to be used in these async scenarios where you're getting data off of I/O, network connections, etc. But of course, you can switch from that memory of byte to a non-async method at any point and start working with that same data as a span. But once you've worked with some of the data, you just advance the pipe writer by how much you've written and then flush it. And as soon as you flush it, that awakens the reading end that will be sitting there waiting. So on the reader, we called read async, and that will then just asynchronously await data being available from the pipe. So it's non-blocking, and eventually we get back a read result once some data's flushed in for us. We can access the buffer on that read result, which comes back as this read-only sequence of byte. So why a sequence down here and a memory on the way in? And the reason is, ahead of time, the pipe doesn't know how much data is going to fill it. Typically, if you're reading off of the wire, for example, then you might be dealing with chunk data and you don't know the content length yet. And so what it does internally is it will rent a block of memory and start filling it for you. And if you're keeping up with the reading and the writing, then that might be sufficient. But if at any point the reading end slows down and isn't actually processing all of that block in time, then it will just rent another block of memory and then another block of memory and keep filling it. And then on the reading end, what it gives you is this essentially a linked list of those blocks of memory as this read-only sequence, and gives us a way to view that data in the correct sequence. So the example that sort of demonstrates usage of this, again, similar to the last one, same sort of microservice, we were dealing with retrieving objects from S3. In this case, it was a tab-separated file, so we wanted to get 3 columns of data from separated file and index them into Elasticsearch. So I shall show you the before code. I didn't write this. I'm going to tell you that in advance because you might spot the problems. So this is roughly what the original code was doing. So here I'm using a file stream in this demo app, but it was basically an S3 stream from the S3 API instead. It needed to be decompressed because it was zipped, gzipped for decompression. And then this is where the code gets a bit interesting. So it then, after decompressing, it creates a new memory stream, and it copies from the decompressed stream into the memory stream. It then calls toArray to get the entire bytes from that memory stream, and then called getString to then get the string representation of that file. And then it was passing it into this parser thing. Now, the reason it was doing that, I think, at the time, is that it was using this library called tinyCSV parser that I think only took string inputs at one point. At least that's the explanation I was given, and I will trust the engineer did this for a good reason. But if you're looking at this code, you can probably spot where this might allocate. We're copying memory, we're creating a new array, which again is copying. We're getting a string that represents the entire contents of a large file. So all of these allocations that occur here also occur on the large object heap, because typically these files are about 10,000 rows each time. So the new code that we switched to, slightly more complex if you look at the length compared to the last one. But what we did instead was, we still need the decompress stream, but as soon as we've got that, we use this pipe reader create here to just create a reader over that stream. So that gives us a pipe reader that's accessing the stream as the data becomes available. And so we do the read async, we access the buffer, and as soon as we've got the buffer, we can call parse lines to see what lines we've got. And so this is dealing with that read-only sequence that was coming off the pipe reader. And it uses a sequence reader as a helper type that allows us to more easily parse through these sequences, because we have to deal with a scenario that we might have one block of memory or multiple blocks that we have to work through. So the sequence reader deals with that. And so it gives us this convenience that we can just loop through the reader until we've read everything. We can try and read out an entire line. So what we want to essentially get is one line of the file delimited by the new line. So if it finds a new line, give me the span of that file or of that line that represents the data that I can then process with parse line down below. And then parse line is just manually doing what that tinyCSV parser library was doing, where it's basically accessing the free tabs or columns of data that we actually care about. So it basically finds the index of the tab character, checks if that current tab count that we're at is a piece of data that we care about. And if it is, at that point, it does get the string by slicing the line from the current position to where that tab appears. And that gets us our string that we need to populate our object to go into Elasticsearch. So it only does that for the 3 columns we care about, 0, 1, and 10. And as soon as we've reached that, we actually then just break out of this loop, because we're not going to go past the columns that we care about when we're reading that line. That's pretty much what it does. And I'll show you the before and after of that. So that's just switching to those pipelines and, again, span-based optimizations. So the original code versus the new code, about 81% quicker. We weren't going for speed. The reason we investigated this service was that it was running as a container. We had memory limits set on it, and quite regularly it was hitting those memory limits and killing the container. And so we constantly seemed to find ourselves increasing the container limits for that container. And that's why we looked at it, we saw that code, and we then realized that actually, yeah, by switching to this new version, we could remove 97% of the allocations just by switching to something that wasn't allocating as much. And when I did a profile on that, it was about 2.85 of that with the data that we actually needed, the strings that we did want to push into Elasticsearch. So there was about 0.45 meg of overhead. Some of that comes from the pipe reader types and the sequence reader types. I still do want to check and see if I can get that down any lower, but this is a good example of like sometimes stopping when you've done enough is perfectly fine. We'd solved the main problem. That 0.45 meg of overhead is insignificant compared to the problem we started with, and so we didn't feel the need to go any further with this one. So we've got a few minutes left, so I'll very quickly try and go over the System.Text.Json stuff with a quick demo of what that can do for your code. So these have been in the box since .NET Core 3.0. So traditionally, most people will probably be familiar with Newtonsoft.Json for doing JSON parsing. Microsoft introduced this as an in-the-box API in 3.0 to start giving us a new version of JSON parsing that could take advantage of these new high-performance techniques. And so it gives us 3 levels to work with. We can work at a very low level with directly with kind of UTF-8 bytes for the JSON reader and writer. We can work at a middle level when we're reading using this JSON document object model that we can then process our way through in a kind of read-forward fashion. And then we also have a regular kind of serializer where you can just say, give me an object and serialize it, or give me some JSON and deserialize it into an object. Even that new higher level one is going to be more optimal than using Newtonsoft.Json just because it tries to avoid allocations behind the scenes as much as possible. But the real gains come if you really need them from those low level types. So the example I have for this, again, similar scenario to the last one. I was working on a scenario where we were bulk indexing some data into Elasticsearch. When you do that with Elasticsearch, it gives you a response back that tells you, did any of the maybe 100, 1,000, whatever it is you're sending in operations, the indexing operations, have an error. And then it also gives you a summary for each operation as to what the status codes were for them. And so what we wanted to do is just find out if any of the data we tried to index was failing so that we could track the IDs and essentially dead letter those items and deal with them later. So I'll give you a quick tour of the before and after code. So the original code is really terse. It was using Newtonsoft.Json. That's all the code there is. Ultimately, it was getting to the point where we had a JSON serializer, deserializing the JSON response that comes back into this type, which has the length of time it took, whether or not there were errors, and then for each item, each indexing operation, what was the result. And then what we do is check that errors property, and if there's no errors, it's given us a false on that errors property, then we can just say that, yes, this was successful, and there's no IDs to return. Otherwise, we have to process those items to find the IDs of the ones that failed. So that is pretty easy code. Now, the new code, I'll grant you, is a good example of where moving to the higher performance code is less terse, and this would be less maintainable, right? But if you need the performance, then this is the kind of thing you might end up doing. So what this does that's different is we read a stream, in this case directly, and we go into this parse errors where we've read some data off the stream. We just use the rented array from the ArrayPool for that buffer for the streaming in this case. And so what we do here is we switch that low-level JSON reader type. And at that point, what we can do is basically ask it to read through the bytes that it's received, giving us each JSON token as we reach it. So this reads forward a JSON token at a time. But we track a bunch of states. So you can see I'm passing in a bunch of my own state in here, mostly as by reference, as well as this JSON reader state object, which allows us to make that UTF-8 JSON reader re-enterable. So the state tracks where it is in that JSON structure. So if you're getting data in chunks off of the wire, you can start processing the JSON and then return to this method later on to continue with the next chunk. And the basic premise of what this code does is it switches on the JSON token, and so I can kind of track my way through that expected JSON data that I'm getting. So am I into the start object? Am I into the array? Have I reached certain properties? So does the token value text, so the string, match this predefined, in this case, this U8 here basically converts this string literal into a UTF-8 JSON byte as a read-only span, again using that same technique to kind of cache those in the binary. And so what this does is basically track when we've read the ID properties and the status properties off that item, checks if we've read like a true or false result, for example. And the key really is down here that once we've checked that errors property on the message, and if it's false, i.e. there's no errors, we can stop processing the rest of this JSON data. And so even further up the code, here, we do another check and we break out of this other while loop here as we're reading that data off the stream. So we can short circuit in the happy path where we generally expect all items to have been indexed successfully. And that's kind of the crux of the improvement there. I'll show you the numbers before we switch to the last couple of slides. So in the unhappy path, where there are errors on the response, then we still see that there's a 67% reduction in execution time, and still a very good reduction in the overhead of the JSON parsing. We still have some allocations because we need to capture all of those IDs of the failed messages or the failed operations. And so that means we've saved 84%, but not completely saved our allocations. But for the 99% case where we expect everything to be indexed successfully, because of that early exiting, as we've read the first few tokens of JSON, which is roughly the first, I think, 20-something bytes of JSON data, we exit really early. So now we've exited in 200 nanoseconds from that processing loop. And we've got 0 allocations now because on that sort of success path, there's nothing to gather. We don't actually need to allocate any instances of objects to track that data. And so very quickly, we can get some real gains with that UTF-8 JSON reading approach. So to wrap up in the last minute or two, maybe you like what you've seen today and you want to go and get business buy-in. How do you do that? I recommend starting with quick wins. So think of services you know have performance issues within your organization. People complain how long they take or how many instances you have to run to process your data, that kind of thing. Then use a scientific approach to work out the gains, and then change that into a monetary value. So the main problem of going to a business owner and saying, hey, I can remove all byte allocations on this code path is that business owners probably don't really care what that means or might not understand. But if you can show them monetary value, it tends to make a bigger difference. So give them a cost-to-benefit ratio. So all of the stuff I've shown you today, plus other techniques, went into one key microservice we had, that one that was dealing with 18 million messages a day. And through various experiments with these small changes, it worked out we could save about half of the allocation and roughly double the per instance throughput of those processing services. And what that led to is reducing 1 VM a year that we needed to run that particular microservice as a container. Now, $1,700 on its own might not be worth the engineering effort that it took to introduce this, but we had hundreds of microservices doing very similar things, and we could reapply this pattern. And so this then can start to scale. So these kind of gains can really have an impact as you move to multiple instances where you're applying these same kind of techniques over and over again. So in summary, when you're doing this kind of stuff, don't assume, don't make assumptions, measure with profiling tools, measure with benchmarking before and after doing things. Be scientific, so small changes each time, have a theory, validate the theory and move on. Focus on the hot paths, because they're the areas that you're going to get the most gain from. Don't copy memory, so using things like span to just slice your way into existing memory is a very good way of reducing allocation overhead. Do use ArrayPools where it's appropriate to do so to avoid those short-lived buffer-type allocations. If you're doing anything with sort of regular streaming of data, then and off. No, I'm on. Yeah, consider System.Text.Json APIs as a quick swap out for Newtonsoft JSON for some wins. If you want to go deeper, this book by Conrad, there's a new edition coming this year. I highly recommend it. It's about that thick. It's about 1,000 pages in English. It's fantastic to read. It's also great to carry around as a weapon. And it has all of the stuff I've shown you today and more. So that's it. I'll give you the link to the slides. I don't have time for questions, but I'm happy to kind of answer them off to the side afterwards. Thank you.